Okay, shall we start today's colloquium? So today's speaker is Monika Aidelsburger, a professor of Ludwig Maximilian University of Munich, and she's a group leader of. She's right now a group leader. I'm sorry. She's a great group leader of a synthetic quantum group matter of that university. She was originally a student in that university, supervised by Emmanuel Prof, and took a PhD in 2014, I guess. And after that, she joined French École Polytechnique group as a postdoctoral researcher, and then returned to Munich in 2017 as a faculty member. And then in 2019, she was promoted as a professor. And right now, she's working very actively on the cold atoms, including the very advanced topics, including many-body localization and Hilbert space fragmentations. And so right now, today she's going to talk about some results on the quantum simulations engineering on probably related to Hubbard models and to gauge theory. So could you start? You can ask any questions during the talk, and the talk will be up to probably 1 hour, I guess.
Okay, yeah, thank you very much for having me. Yeah, I'm sorry I changed the title, but it's actually still the same topic. So the idea is to talk about quantum simulations with neutral atoms and optical lattices, and explaining a little bit what techniques we have developed over the years and how we can extend the range of model Hamiltonians that we can access. So naturally, we can study Hubbard models, but then the idea would be to explain a little bit how we can modify these systems in order to study artificial gauge fields and gauge theories in particular. Okay, so let me just very briefly start by introducing the experimental platforms. I just have one slide on that just to explain a little bit how the system looks. So for these quantum simulation experiments, typically we first laser cool the atoms to very low temperatures, using evaporative cooling down to nanokelvin regimes, where we can either work with bosonic atoms or fermionic atoms. So we either form a Bose-Einstein condensate or a degenerate Fermi gas. And then we prepare them in optical potentials based on the AC stack shift. So we have far detuned laser beams. And for instance, in the simple configuration that you see on this slide, where we have 2 counter-propagating laser beams, they can form the periodic potential energy landscape, where the distance between neighboring sites is on the order of the wavelengths of the beams that we use to form this lattice. And then by overlapping many of those, or by using a different interference pattern, we can form different energy landscapes. And this is a simple example in a 2D plane. If you overlap 2 of these standing waves perpendicular to each other, you would form a square lattice geometry. And if the atoms are cold enough, we can adiabatically load them into such a lattice potential. And then the dynamics is described by Hubbard models. So just by 2 simple parameters here, in this case, I wrote it down for bosonic atoms. But as I mentioned, we can also work with fermions or include additional internal degrees of freedom, so make this Hamiltonian a bit more complex. But the general theme is if we adiabatically load the atoms in such a lattice, we can study Hubbard type physics. And as you know, so there's the kinetic energy term that is proportional to the tunnel coupling J. And then there's an interaction energy term, which is proportional to the Hubbard on-site interaction energy U. Now, the nice thing about these systems is that they are very well isolated from the environment. So we prepare these cold gases in a vacuum system. And there's really no contact to a thermal bath. So the only thing the atoms interact with is the potential that we generate with the laser beams. And moreover, because the length scale are quite large, so the distance between neighboring sites is on the order of a micrometer, we can build microscopes in order to directly take snapshots of the atoms in the lattice and measure their density distribution. So for instance, on this picture here on the right, this is one that I've taken from our cesium lab, where you see each individual cesium atom as this bright spot on the camera. So each individual cesium atom emits like a few thousand photons, which we can then image on a camera. And this allows us then to measure other observables that in conventional bulk quantum gas experiments you would not have. We can measure density-density correlation functions. We can look at fluctuations, full counting statistics. And this gives us a more direct insight into the dynamics of quantum systems. Now, the class of experiments that we do, you can separate in 2 main categories, I would say. So the first one deals with ground states. The idea is that you have this cold degenerate cloud of atoms that you then adiabatically load into a lattice, which implements a certain model Hamiltonian of interest. And here the idea is to stay at very, very low temperatures. And here I've taken a picture from Markus Greiner's lab where they have looked with a microscope on the Fermi-Hubbard model at filling 1/2 in order to directly see antiferromagnetic correlations. And then because we have control over the model Hamiltonian, we can change the parameters and see how the ground state properties change as a function of these parameters. In the simplest case, that would be U over J, which has been used for bosonic atoms in order to study the superfluid to Mott insulator transition. The second big class of experiments deals with dynamics. And because our systems are so nicely isolated from the environment, we can use that in order to address fundamental questions regarding the thermalization of isolated quantum many-body systems, for instance. So here the idea is that we prepare very well-defined initial states that we know how to prepare with high fidelity. So for instance, that would be a certain initial charge configuration, a Fock state. And then we quench the system, we turn on the Hamiltonian, we turn on the dynamics, and see how the system evolves. And because we now have these quantum glass microscopes, we can look at how information spreads in the system. So we can look at correlation functions, how they build up as a function of time. Now, there's one thing I want to emphasize. So these quantum glass microscope experiments, they do analog quantum simulation. And just to emphasize what's the difference, we are implementing this Hamiltonian H directly. So this Hubbard model, the parameters J and U, they are implemented via the microscopic degrees of freedoms of the atoms in the lattice. The alternative way would be to use a digital approach to not actually directly implement the Hamiltonian, but trotterize it and then decompose it into gates. So far, I would say that the analog quantum simulation experiments still outperform the digital ones just because we don't accumulate errors in terms of the gates, which have a finite fidelity. Now, the disadvantage, if you want, is that we can only implement certain Hamiltonians, and we have to develop new techniques in order to engineer different types of Hamiltonians. So it's not a universal device. We cannot study anything that we are interested in. Okay, so let me say a few words about quantum gas microscopy, also to tell you a little bit where I think we are at the moment and what still needs to be developed or what people are interested in developing nowadays. So the basic idea of these quantum gas microscopes is that you trap a cold cloud of atoms in a 2D plane. So here you see a vertical lattice in the Z direction, and these blue balls indicate that the atoms are trapped only in one node of this lattice. And in this plane, you can then have different types of potentials, for instance, square lattice, as depicted here in the zoom in, but it could also be a graphene type lattice or a leap lattice or any other type of lattice in this 2D plane. Now for imaging, we have to freeze the atomic distribution in this lattice, so we make it very deep. And that means for us a few hundred microkelvin in depth. And the reason for that is that for imaging, we want to scatter many photons, but scattering photons heats up the atoms, and we have to make sure that they are not lost from the trap. So we need to scatter photons and cool at the same time. So in the simplest case, we use some type of Doppler cooling laser beams that scatter and cool both at the same time. There are more sophisticated techniques like sideband cooling that could also be used. And then these photons that are scattered from the atoms are collected with these high NA objectives and then imaged on a camera. And then you get pictures like this, similar to the one that I've shown you before, where each individual atom shows up as one of such a bright blob. And the size of this blob is given by the point spread function of the imaging system, so the resolution of the imaging system. And for taking statistics, now you have to take many of these snapshots. For instance, in order to get to the mean value of the local occupation, you would take many of these snapshots because the imaging process projects it onto the Fock basis. But then you also have the full counting statistics. So you have all these individual snapshots. So you also have the occupation distribution side resolved. And that is, of course, very nice. In combination with more complicated potentials like superlattices, we can even look at other observables. So we are developing right now tools in order to also measure local currents, for instance, and get current correlations in these systems. These microscopes nowadays exist for many different species. I've just taken a few examples to visualize how these images look like. They are different in certain senses. So here you see a triangular lattice, most of them are square lattices. And it has been started with rubidium and alkali atoms, but nowadays they also exist for like more complicated atoms like ytterbium, 2-valence electron atoms, and fermions. So this is just a small set of examples. And so the question is, since we have all of these microscopes available, what is next? So what do we think as an experimental community, what needs to be developed over the next few years? And in order to give you my take on this, I've summarized a couple of points. So the first one I would like to mention is that in order to have a good fidelity of quantum simulation, we want to make these systems homogeneous. So you see, for instance, in this picture with the orange atoms, the potassium atoms from the Zwilling group, that usually there's also an overall confinement. So there's a density distribution in the trap that is not homogeneous. And the reason is that we need to keep the atoms in place. And this is typically done with the Gaussian laser beams, which generate an additional harmonic potential. But this also means that actually, if you look locally in the lattice, it's not a homogeneous potential, but there are potential energy difference between neighboring sites. And that can complicate the simulation that you want to do, because ideally you want to study like a homogeneous lattice potential and then controllably add maybe disorder or something else to the system. So we have to develop techniques in order to make this flat. And I will show you a picture on the next slide on how we do that in our lab. The second thing concerns the fidelity of the initial state preparation and detection, and that mostly concerns temperature and energy scales. So especially if you think about probing ground state physics, we need to be able to go close to t equal to 0. And this is not always easy to do. For instance, it's a known challenge in order to study the Fermi-Hubbard model and achieve lower temperatures. The same is true for dynamics, because you want to have well-defined initial states. So you have to be able to prepare them with very high fidelity. And then, as I already mentioned on the previous slide, since we are doing analog quantum simulation, it's important to know what type of Hamiltonians we can actually study. And it's important to develop new techniques in order to increase the class of Hamiltonians that we can access. Now, regarding the first point of engineering large homogeneous systems, I want to share this picture from our cesium quantum gas microscope, where we have actually developed techniques to flatten the potential. So in this case, the atoms are actually not held in the trap by a harmonic trapping potential, but instead we create a box. So we have repulsive walls that we project into the atomic plane in order to confine the atoms. And this basically decouples the confining potential from the lattice potential. So we can make the lattice very, very homogeneous and keep the atoms in place using this box. And what you see here is a system of about 50 by 50 lattice sites. So it's about 2,500 atoms, a little bit more than that, with very high filling. So we formed a Mott insulator in this box, and we achieve fillings on the order of 98%. And just very briefly, the way we do it, we shape this potential using digital micromirror devices. So that is a device that consists of about 1,000 times 500 little tiny mirrors that we can switch on and off. And we use this in order to shape the intensity profile of a laser beam, which we can then project into the atomic plane. And specifically for repulsive potentials, now we can make the square region dark, and the potential will only project it outside. So in this dark region, we have the light, which repels the atoms from this outside region. And on top of that, if there's a residual curvature, we can use this in order to compensate a residual curvature in the trap. So here you see how we do that. That's for a superfluid, where initially you see there's a minimum actually in this trap towards the right. And then by applying a compensation algorithm, we can make the bottom of the trap flat. So this is very nice. And we have actually started now to benchmark the performance of our quantum simulation experiment by looking first at out of equilibrium dynamics. So this was already mentioned. We have performed a couple of experiments already along this direction, looking at localization in a many-body localized regime, and also looking at weak ergodicity breaking phenomena such as Hilbert space fragmentation and tilted Hubbard models. And this is, of course, something that we can also study in our microscope experiment now, which has these large homogeneous systems. For now, one of the first experiments that we looked at is to look at the thermalization of a very simple initial state, which is an initial Fock state where every other site is occupied by one bosonic atom. And I should also say that the ratio U over J in the bosonic Hubbard model is tunable using Feshbach resonances. And in this case, we do something very simple because we just want to benchmark the performance. We go to the hardcore limit. So U over J is on the order of 10. So we can consider that there are never two atoms on one side. So the fraction of doubly occupied sites is minimal. So we have this initial state. And of course, if we now turn on the dynamics in this homogeneous lattice, we expect the system to thermalize. So if we just measure the amplitude of this charge density wave, it will quickly decay as a function of time. And this has been done in many early experiments looking at the decay of the amplitude of such a charge density wave. Now, because we have access to local observables, we can do more. We can look at the spreading of correlations. So what we plot here is density-density correlations between neighboring sites I and J as a function of distance. And this is here shown for the first few tunneling times, up to 5 tunneling times. And because this hardcore boson model in 1D maps onto 3 fermions, you expect this very nice ballistic light cone. And the slope of this light cone is given by the Lieb-Robinson bound, which is proportional to the bandwidth of the lowest band. So this is actually given by a velocity that scales with 4J in this one-dimensional system. So this is the simplest case, but now from that on, we can of course tune away from this easily understood point. We can make the interactions finite, we can make them soft core, we can couple more than 1D chain, which will change it from ballistic to diffusive. We can look at full counting statistics, and then we can also add controllable disorder in order to study localization, or to add a tilt in order to study Hilbert space fragmentation in 1 and 2 dimensions. So this now opens the door to a variety of different thermalization experiments that we can perform in our quantum gas microscope experiment. And something that I want to emphasize here is you see that the correlation spread over distances up to 18 lattice sites. And in order to be able to see that, of course, you need a large system. And this has been taken in a system where the chain has a length of up to 40 lattice sites, or sometimes even 50 lattice sites. All right, so there's one additional thing that I want to mention, which is important for quantum simulation experiments. And the key tools or the key aspects that we are working on is to increase the repetition rate in order to have more access to statistics, and to increase the local control, which actually helps in increasing the repetition rate, but it's also useful in order to increase the class of model Hamiltonians that we can access. So let me first say a few words about the repetition rate. I've showed you these images, which you also see on these slides, that we can take snapshots of our quantum many-body system. So we have this access to the local distribution. But in order to get statistics, you want many of those. So the question is, how long does it take to generate one of these images? Because after we have taken this image, the sample is destroyed and we have to prepare a new one. And here I've already put this on the upper left corner. One snapshot takes on the order of 20 seconds, depending on the experiment. So people have also managed to reduce it to a few seconds. Some experiments still take up to a minute. And the reason why this takes so long is because we have all these different laser cooling steps that happened in between. So each experimental cycle actually starts with a hot cloud of atoms that is diffusing into this vacuum system. And then we have different laser cooling steps. So here there's a first laser cooling step in a magneto-optical trap. And for our cesium lab, it also includes Raman cooling, where we reach microkelvin temperatures. This laser cooling step is actually quite fast. So it's on a millisecond time scale. That's actually not the problem. There is, for quantum gas microscopes, often a transport section as well, meaning that from a first laser cooling chamber, we transport the atoms into the second science chamber, because there we can have a better vacuum, and which increases the lifetime of the system, and better optical access. Now, this transport can take a few seconds depending on how it's implemented. So for instance, you can have like a magnetic trap in an overlapping coil configuration that you move adiabatically from one region to the other. This can take a few seconds. In our case, we do it optically, which takes only 30 milliseconds. So that's already very helpful and not really the limiting factor in our experiment. Now in the science cell, we typically perform further laser cooling, and this involves evaporative cooling techniques. So the idea is you have the atoms trapped in a cross dipole trap, for instance, in a harmonic trap, and then you successively remove the hot atoms and let the remaining ones rethermalize. And this process can be slow. It easily takes 10 to 20 seconds for this evaporation in order to form a Bose-Einstein condensate or a degenerate Fermi gas. So that's by far the largest budget regarding the times that you need before being able to perform the simulation in optical lattices and then take a snapshot, which then again is typically also only on the order of a few hundred milliseconds or 1 second. So what we try to do in order to speed up the cycle time of these systems is to get rid of this evaporative process. And this makes the step towards local control, because now the idea is to actually only use laser cooling in order to generate the atoms in the lattice. And many groups are working on this. I've taken here one example from Adam Kaufmann's group, where they have laser-cooled atoms in an optical tweezer array and transferred them into an optical lattice in order to do simulations of Hubbard-type physics. Okay, so how does that work? You see in the schematic these elongated tubes. So the idea is to form an array of tightly focused laser beams, where then you can do sideband cooling in order to go to the absolute ground state of this tightly focused trap. What happens if you do that is this is extremely fast. You can go to the ground state, but you end up with a statistical occupation of the traps. So this is shown here on the left. So each green spot is one atom. You would have a two-dimensional tweezer array, but you statistically have an atom in the trap or no atom in the trap. So it's projected onto zeros and ones. Now, if you want to use that for a quantum simulation of many-body physics in the Hubbard model, that's of course bad because you don't have control over this occupation. So what needs to be done in addition is actually to rearrange them. And that's an example I've taken from Michel Lukin's group. In this case, this rearrangement has been done for Rydberg atom simulations, going to the simulation of spin models and quantum computation. But the idea is exactly the same. In either case, if you either want to do spin models with Rydberg atoms or simulations of Hubbard models, you need to be able to rearrange the atoms. Now, for Rydberg systems, you're actually done after this step. That works beautifully and has been shown now by many groups. For Hubbard models, you now have to add an additional step. You have to transfer these atoms into the lattice, and you have to cool them down again to the lowest vibrational state on each side in the lattice in order to be able to study coherent tunneling dynamics. So this is a little bit more challenging to do. And this has been achieved here for strontium atoms in the Kaufmann group. And we are actually working with ytterbium atoms, fermionic ytterbiums, in order to realize these systems. And then this actually brings down the cycle time to a few hundred milliseconds. So you go from something that takes like 10 seconds to something that takes on the order of 100 milliseconds. And of course, that's very beneficial if you want to take 1,000 images to study the statistics of occupations, for instance. Of course, this brings down the experimental considerations and timescales down by a factor of 100, which helps a lot. Okay, the second question I want to address is what type of Hamiltonians we can simulate. And I've shown you in the previous slides that what we naturally do is Hubbard models, because we can adiabatically load the atoms in these lattices, and then the microscopic parameters are given by the tunnel coupling and the Hubbard interaction energy. What we have been working on for some time is to extend this in order to be able to also study topological phases of matter. And I just want to briefly summarize some of the experiments and techniques that are out there in order to study topological and specifically quantum Hall type systems in cold atoms before moving on to the techniques that we are thinking of developing for studying gauge theories. And I should say that the class of models that we can access is a small subset of all of these topological materials. It's actually very challenging to make Hubbard models topological. And many of the techniques have been focused on realizing artificial magnetic fields to study integer and fractional quantum Hall physics, as shown here on the left slide. And you can already see by looking at this schematic drawing and remembering how a quantum Hall effect arises in electronic systems, that this is quite challenging to do in cold atoms because we cannot simply apply a magnetic field and study Lorentz type behavior. Our atoms are charge neutral, so we have to find other techniques in order to mimic this quantum Hall type system. And this is also what I want to use as a starting point in order to explain a little bit our thought process for quantum simulation of certain model Hamiltonians, because the way it works is mostly following the same line of thoughts. So whenever we are interested in studying a certain many-body Hamiltonian, we typically first ask the question, like, what's the simplest model Hamiltonian that captures, in essence, the physics that we are interested in? So if you think about artificial magnetic fields or studying electronic systems in the presence of a magnetic field on a lattice, what happens is that the usual non-interacting type binding Hamiltonian, where we only have a hopping matrix element J between neighboring sites, gets modified. So we have an artificial magnetic field present, and the way it shows up in our discretized lattice Hamiltonian is according to the Piot substitution, which in some sense is just a discretized version of the Aharonov-Bohm effect. So we have these complex hopping matrix elements between neighboring sites that are associated with phases. So in the end, if you want to perform a quantum simulation of this type of Hamiltonian with complex phases, what you have to be able to do is develop a technique that allows you to make these tunnel couplings, which are typically real, complex. And the next step essentially is to focus on that. So as an experimentalist, you can now forget about the electronic system and the magnetic field and how it would originate in a true solid state system. You focus on developing a technique that makes this tunnel coupling complex. And then if we go around a closed loop and compute the Aharonov-Bohm phase, we can interpret this as a magnetic flux, even if we are actually working with charge neutral bosonic atoms. And something that I also want to highlight is that once you have such a technique and it actually works, you can then generalize it because you're not bound to the limits of a real magnetic field. So for instance, you can go to extreme limits where you can engineer artificial magnetic fields that would correspond to fields of thousands of Teslas in a real solid state system. Since you are just imprinting phases, there's nothing that limits you in terms of the strength of the magnetic field that you can apply. Okay, and just very briefly, the technique that we have developed over the years in order to realize that is Floquet engineering of periodic driving. So the Hubbard model that we realize in our lab has two parameters, J and U, and we can vary them periodically in time. This has been mostly done so far with non-interacting systems. So there we would play with the tunnel coupling J or on-site potential that we apply in addition to our homogeneous lattice potential. Now, the period of the drive in this case is T. And if we go to the fast driving limit, the stroboscopic time evolution is governed by a Floquet Hamiltonian. So here you see the Floquet evolution operator, where capital T is the period of the drive. And if we look at integer multiples of the modulation period T, this is described by a time evolution operator, which has this new effective Floquet Hamiltonian appearing in the exponent, which is time independent. And in the high frequency driving limit, this Floquet Hamiltonian can be computed perturbatively by making a series expansion in powers of 1 over omega, where omega is a very large quantity. And to lowest order, this Floquet Hamiltonian would be given by the time averaged Hamiltonian of this time-dependent system. Now, this also means that we are actually working in quasi-energy space. So we have this Floquet quasi-energies where here you see one Floquet Brillouin zone. For a two-band model, we would have the blue and the orange line. And because the quasi-energy now appears as a phase, it's only defined up to integer multiples of h bar omega, where omega is the driving frequency. So we have this infinite series of copies of this two-band model. And I will not talk about this today, but this also gives you additional opportunities in order to engineer novel topological phases that do not have any static analog, because you can have gap closings between Floquet Brillouin zones. So you can engineer so-called anomalous Floquet systems where the Chern number of the band is 0, but nonetheless you have topological edge modes in the system. And this is something that we've studied in driven hexagonal optical lattices. And we are still looking at this in order to study now the interplay between topology and disorder. Okay, so in principle, now the idea is to develop periodic modulation protocols that then allow you to engineer new Floquet Hamiltonians with interesting properties. And the first thing that we have looked at, just to give you an example, in order to see if that actually works, so if we can actually mimic electrons in the presence of a homogeneous magnetic field, is to look at cyclotron motion. So you know that electrons would move on cyclotron orbits in the presence of a homogeneous magnetic field. Now we have charged neutral atoms that are trapped in a lattice, but still you can try to recreate that. And we have done that on a small lattice of 4 sites. So you start with the atom localized on one specific point in the lattice. So in this case, we track the mean position along Y and the mean position along X. It starts at a certain point, and then it does actually follow a sort of cyclotronic motion in the lattice, which in this case is highly discretized because the lattice only consists of 4 sites. But now people have also engineered that with internal states. So one of these 2 lattice axes is actually replaced with Zeeman sublevels in an atom. And there you see now this nice, beautiful cyclotron motion. It's exactly the same idea. You imprint phases on the tunnel couplings. And this is an example with dysprosium atoms, which I've taken from Sylvain Assomben's group at Collège de France, which they have published in 2020.
So
this is just to show.
Can I ask one question? So I probably missed how you have created the flux inside this 4 site.
Yeah.
Charge neutral atom, right? So just make some kind of a flux or some phase factors to create that kind of phase. So how did you implement that in your devices?
Yes, so the easiest way to see that is actually in this synthetic dimensions, where you have 2 internal states that are coupled. The real space implementation is similar. So I think it's still a good picture. So let's say you have 2 internal states, 2 Zeeman states. A priori, they are not coupled, but you can couple them by 2 photon Raman transitions if you add additional laser beams. This 2 photon transition introduces a coupling between these 2 states, and this is given by the Raman coupling, so the Rabi frequency, which is complex. So if you compute the Rabi coupling, it involves the phase of the laser beam. So now if you have the phase of the laser beam imprinted on the coupling, it depends on the position because the phase front advances as a function of space. And this phase is then imprinted on the tunnel coupling, which then shows up as a flux per plaquette.
So you just make use of another laser beam to create some sort of a gauge field, U1 gauge field. I see. I don't understand the detail, but anyway, I probably got the overall.
I could give you more details after the talk. I skipped that here because I wanted to talk a bit about lattice gauge theories, but I'm happy to. It's easy to explain like on a slide in a few words.
Okay, thank you very much. So let's go ahead. I mean, later on. Yes. Okay.
So having this flux and this periodic driving technique then enabled the realization of 2 main model Hamiltonians, specifically the Hofstadter model, which is the square lattice in the presence of a homogeneous magnetic field, which has this nice single particle Hofstadter butterfly spectrum, and which hosts many different topological phases that one can study. And the second one being the Haldane model, which does not have a homogeneous background flux, but a staggered flux contribution in the unit cell. So we have nearest neighbor hopping that is real, complex next nearest neighbor hopping, and the sublattice energy offset delta AB between neighboring sites, which allows you to tune from topologically trivial to topologically non-trivial regions in the phase diagram as a function of the sublattice energy offset and the complex phase on the next nearest neighbor hopping. So in this case, it's a little bit more non-trivial to see how the Haldane model emerges. This is because the periodic driving actually breaks time reversal symmetry in the lattice. And if then you compute the lowest order of defective Fouquet Hamiltonian, you see that there are these complex hoppings that appear on the nearest neighbor tunnel coupling terms.
Now, sorry to interrupt.
Yeah.
Can we also implement a spin-orbit coupling in this such an artificial settings, like which might also have a maybe topologically non-trivial phases? Right?
Yes, so there are other groups that have worked on the implementation of spin-orbit coupling and Rashba spin-orbit coupling Hamiltonians. They involve also different internal states. So these examples that I've shown here, they concern atoms that are prepared only in one internal state, and then they map onto these kind of systems. If you engineer Hamiltonian, it's actually what I explained previously in how the flux is generated. This is actually already like a first step in order to spin-orbit coupling, because you have like a flip of the internal state and you imprint momentum by this 2-photon transition. So this is the basic ingredient that you need for spin-orbit coupling. So indeed, you can also do that.
how can we implement the spin degrees of freedom in these settings? I mean, maybe
the spin degree of freedom in our case is really different internal states of the atom. So this could be in the simplest case Zeeman sublevels or other electronic states.
Oh, I see.
Yeah.
Okay, thanks.
So exactly what you see actually on this example that I've taken from the dysprosium lab, where you see these nice cyclotron orbits. This is essentially the ingredient of spin orbit coupling. These internal states are the Zeeman sublevels, which for dysprosium you can have 16 different levels that you can couple.
Nice. Okay, thanks.
Okay. Yeah, sorry that I'm going a bit fast over this. So in these systems like the Haldane model and the Hofstadter model, we were specifically interested in directly characterizing the geometric and topological properties of the band. So in this non-interacting limit, it's very easy. You can define a topological invariant for each band, which is the integral over the Berry curvature. And the Berry curvature is defined in quasi-momentum space, so Qx and Qy. And it's defined as the winding of the cell periodic Bloch functions as a function of Qx and Qy across the Brillouin zone. And what I want to highlight is that apart from the many techniques that have been developed in cold atoms, you can actually directly reconstruct this local quantity of the Berry curvature. And this is a picture from Christoph Weitenberg's lab in Hamburg, where they have done that with a fermionic cloud that was trapped in a hexagonal optical lattice. So the solid line marks the Brillouin zone of the hexagonal lattice. And here you see a map that was extracted using state tomography of the Berry curvature of the lowest band, which shows here these blue and red regions, so positive and negative regions. And then you can get the Chern number of the band simply by summing up all of these values. In this case, the Chern number is equal to 0, but it has been also demonstrated for bands with non-zero Chern number. And so there are many other techniques. You can do small interferometry experiments in quasi-momentum space. And what we have also done is doing transport measurements in order to measure Hall deflections. So all of this can be done with charge neutral atoms in these engineered band structures. And let me just give you a few additional examples just to tell you a little bit where we are in this field. Now, one of the simplest systems that one can study and extend to interacting regimes, because many experiments have been done in the non-interacting regimes, are so-called ladder systems, where we couple two chains. And here you see an example of two of such ladders that are schematically shown. And you can add an artificial magnetic field to that. So this is what we call flux ladder. And in this case, it has been demonstrated with bosonic atoms. And what you find is that the behavior of bosons prepared in such a flux lattice closely mimics the properties of type 2 superconductors. So we can look at surface currents, which in this case would be just chiral currents around the legs of the ladder. And as a function of the flux or as a function of the tunnel couplings, you actually see a transition from a Meissner type phase to a vortex phase, where you see vortex patterns shown up in the current profile. So this is something that one can study, and it gets more interesting even if you include interactions. And what we are working towards this in our quantum gas microscope is now to have this with control over interactions using Feshbach resonances and a local measure of the current, so to directly reveal the pattern that forms in such a system. The second one I wanted to mention is actually this quantum Hall type measurement, where we implemented transport in order to directly see the Hall deflection of a charge-neutral cloud in the presence of the artificial magnetic field, which allows you to measure the Chern number, and which in principle should also be able to reveal many-body Chern numbers. So if you enter the Laughlin phase or other interacting topological phases, you should be able to use this technique as well in order to see fractional quantum Hall physics. And so far, it has been actually challenging to combine periodic driving and interactions. We believe it's possible, and we are not the only ones. So there has been a first step in this direction, where the group of Marcus Greiner in Harvard has actually managed to engineer a small, like the smallest possible Laughlin state in their system with interacting atoms, here in this case, 2 particles. And we have ideas in order to extend that, so to generate larger systems. And we have also ideas on developing new techniques in our microscopes in order to increase the energy scales which makes it easier to realize these fragile topological many-body systems. But this is a very nice first step in this direction. And from the history of experiments, you can see that it's actually challenging, but doable. So there has been a lot of progress over the last few years. And if you're interested, of course, we can discuss after. So I'm happy to tell you more on this. Now, one additional experiment that I wanted to mention is what happens at the edge. So this connects back to the idea of realizing large homogeneous systems with sharp edges. All these experiments have been done in harmonically trapped clouds of atoms, except the last one. So this two-particle Loveland state, in order to have a controlled state, it has been done in a small box. Now, why is the box important? It's particularly important if you're also interested in topological boundaries. So what happens at the interface between two distinct topological phases. And one way in order to generate sharp edges, again, connects back to the idea of replacing one real space dimension with internal states. So this is what I called synthetic dimensions in the beginning. And here's a nicer slide in explaining this technique in a bit more detail. Here you see a real space lattice axis labeled by X and a synthetic dimension labeled by the internal states, which are labeled by the MF quantum number, which in this case is 3/2, -1/2, and minus 5/2. And this is what I tried to explain in words before. If you now couple these two internal states with a two-photon process, you get this Rabi frequency, which is complex and depends on the phase of the laser beam. So now you have the phase appearing on this bond and on the neighboring one. And because it advances as a function of position, there's a finite phase difference between this link and the next one along X. So this is labeled here as e to the I phi j, where j is the site index. So if you go around one plaquette, tunneling is actually real along the X direction. You pick up a finite phase, which you interpret as a flux. That's the basic idea in synthetic dimensions. In a complete real space 2D system, there's a similar technique. It can be explained in the same way. So if you can keep this picture in mind, it's actually good in order to also understand how we implement a Hofstadter model in real space. Now, the synthetic dimension has...
I can just have some short. So you mentioned that there is a difference in the phase according to the real dimension X. So if you just go toward the synthetic dimension with different X, you acquire different phases due to the Rabi oscillation. So how is it like just to control? You mean that you can control the frequency or something to?
So your question is how this works in a real space 2D system?
As far as I understand, you are preparing a fictitious lattice in the synthetic dimension.
In this case, yes.
Yes. And then I think that you are trying to generate different phase factors in hopping from one blue dot to another green between different X. So if you just start from J and go to green, you have some phase. But if you just start from other blue and to other green, you're going to have different phases.
Yes. So for instance, if you would look at this bond, if you go from blue to green, maybe you pick up a phase e to the I pi over 2.
Yes.
And then here you pick up a phase pi, let's say. And the difference between the two would then give you the flux.
Okay, so you can just arbitrarily control the difference between the phases as you like by controlling.
So it's not arbitrary. That's a good point. It's not arbitrary. So what you see here, the coupling between blue and green is a two-photon process.
Yes.
So it involves e to the I kr of the first beam and the second one. So the phase is actually given by the wave vector difference between the two beams that induce the coupling times r.
Okay, so that difference has some restriction.
Exactly.
But within that restriction, you can just tune whatever you want.
So the overall value of the flux is fully tunable. You can work, it's a geometry problem, and you can work out the phase factors, but it will, in the simplest configuration, always increase linearly as a function of J. So it will always be a homogeneous flux.
Okay, so that's meaningful. Okay, I probably got it.
Okay, so actually having disordered flux patterns would be challenging.
So
I know that there's some interesting.
Much more difficult, you mean?
Sorry?
Because, you mean that the disordered flux pattern is much more difficult than having a uniform flux?
Yeah.
Okay, good.
Because I know there are some interesting models where there's a disorder in the field.
Yes, it's very interesting in a theoretical sense.
Yeah.
Okay.
And so why am I telling you about the synthetic dimensions? Because I actually haven't worked on this. We work in real space. It's just to illustrate how easy it is in synthetic dimensions to study what happens at the topological boundary between the system and vacuum, for instance. Because you have synthetic dimensions, which you implement in internal states, they have a very sharp cutoff. So maybe you can go up to 16 states, as in dysprosium, but then there's the end. You cannot do more. And this sharp boundary then allows you to see, for instance, the skipping orbit. So here they have prepared atoms in the -5 state, which is this edge of this little Hall ribbon. And then you see this nice skipping orbits as you let it evolve as a function of time. But now going back to real space, that's more challenging. So in real space, because we typically have a harmonic trap, everything is smooth. So you cannot easily see these type of edge states. So what we have developed in order to do that is, again, a box potential. So it's a combination of these two things. So here's a picture of the digital micromirror device that I explained on one of the previous slides in order to make this box mod insulator that I've shown from the cesium lab. Here, we use it also in order to generate a repulsive wall. And this repulsive wall serves as a topological phase boundary between the topological system and vacuum, because the repulsive wall introduces a huge chemical potential difference and prevents atoms from going there. And now the question is, how do you generate a good overlap with an edge mode? And here what we do is we work with a Bose-Einstein condensate that we prepare in this tightly focused tweezer trap. And then we move this tightly focused wave packet to certain positions within the trap. And specifically, if we move it close to the edge, we can achieve a large overlap with the edge mode at the boundary. And just to mention, so in our case, the width of this sharp wall is 2 to 3 lattice sites. And here you see the time evolution of this wave packet. So here's the dashed line is the phase boundary. We have the upper part, which has a large chemical potential, so this is blocked, and a small wave packet sits close to the edge. And here the scale by is 10 lattice constant. And now we can let this evolve as a function of time. So it expands, so it disperses, but it does actually not scatter into the bulk. It moves only along the edge of the system. And if you change the chirality of the edge mode, you see it moves in the opposite direction. And there's really no background subtraction whatsoever. We just see a very, very clean overlap of the atoms with the edge mode of the system. And we can also look at the difference images, but you can also clearly see already by eye that depending on the chirality, the atoms either move to the left or to the right. And because we generate now...
Sorry. What is the lattice we consider here? I mean, the one-dimensional lattice or one? Yeah, lattice.
I think
the lattice is in this case actually a hexagonal lattice.
A hexagonal lattice.
Yeah.
If I remember correctly, the hexagonal lattice, I mean, so here you consider some kind of the Howden model, right?
Yes. So this
if I remember correctly, yeah, Howden model has no net flux, right? Because they only have a staggered flux. But you say that it's quite difficult to, implement the inhomogeneous flux,
yes.
right? But
yes. This I can also explain in more detail. In this hexagonal lattice, we perform a chiral modulation of the tunnel couplings. If you do that very fast, you break time reversal symmetry and you realize the Haldane model.
Okay.
To be honest, this regime is actually not the Haldane regime. It's the anomalous regime where we have no Chern number. The Chern number is 0 of the bands, but we have topological edge modes in the driven system between Floquet zones. So this is something that I did not really explain right now, but that's one of these topological phases that we can generate in driven systems that do not have any static analog. And I can explain in more detail, but in essence, what I wanted to show here is actually that we have this technique of directly looking at the dynamics of edge modes, and we have also done that in the Haldane model as well. It just turns out that this anomalous model is much more robust. So it's very easy to see this edge state dynamics. In the Haldane regime, it's a bit more fragile, so we have to work a little bit harder. The technique is a bit more complicated in order to see the edge state in the Haldane model. And the reason for this is that in the anomalous case, you actually have for any energy, any quasi-energy, an edge mode. It wraps around the full Fouquet-Brillouin zone. So it's easy to get a good overlap. In the Haldane, it has only like a small fraction that has a good overlap with the edge mode. And this is at a finite quasi-momentum. So actually, in order to increase the overlap, we also give a finite kick to the initial cloud in order to populate the state.
Okay, thanks.
Okay, you're welcome. And yeah, because we engineer this edge in the experiment, we also can make disk-shaped edges. So this one I like very much because it's actually a bucket. So we block the inner region of this disk, and then the atoms move outside of this disk. So they move at the outside of the bucket, if you wish. And here you see the difference image is a straight line. And now this gives us a lot of opportunities to study the properties of this edge. So now in the last 5 minutes, let me just briefly mention what we are trying to develop right now. And this basically was an introduction into the techniques that we have developed in order to study artificial magnetic fields. Now, I've mentioned already on one of the previous slides, and I'm sorry for that, that's actually a schematic of the Haldane and the Hofstadter, so it's actually the Hofstadter model. I wanted to remind you about the bosonic flux ladder, which shows similar properties as a type 2 superconductor. This somehow always puzzled me in a sense, because the way type 2 superconductivity is typically explained, or at least in my head, is that you have an electronic system, and if you have an additional external magnetic field, there are surface currents that are developed which expel the external magnetic field from the inside of this type 2 superconductor. And it's surprising to me still that you can mimic this type of behavior in a system of charge-neutral bosonic atoms. And the reason why I think it's puzzling is that there seems to be an important ingredient missing, that if the atoms move around in the system, they themselves actually do not generate any fields. The currents do not have any back action onto the magnetic field that is applied from the outside. And this idea of this like kind of missing ingredient, that the atoms that move around, they do not have any back action on the field, motivates a whole new area of quantum simulation experiments where people try to do exactly that. So the first step of having this type of back action would be to implement a density-dependent artificial magnetic field or gauge field. So you want something that actually allows you to change the value of the artificial field depending on the occupation. And using this periodic driving techniques, this can actually be done. So this is one example from Tillmann-Esslinger's group. Sorry, I'm missing the reference here. Tillmann-Esslinger's group from ETH Zurich, where depending on the driving, if you work on resonance in a resonant regime, the Hubbard interaction can move you in and out of resonance. So this is essentially what gives you an additional degree of freedom on manipulating the phase that you imprint on the hopping. So that's the basic idea of implementing density-dependent gauge fields. But you can take that one step further and actually ask, well, how do I properly implement an interplay between matter and gauge field? And this brings you to the general form of lattice gauge theories, which appear in many different areas of physics. So here's a schematic drawing of how you should think of this. So we have the matter that is sitting on the vertices of this lattice, they can hop around. And then on the links, you have additional degrees of freedom, which are the gauge operators. And this looks very similar to a Hubbard model, but it is very different. And the reason is that we need Gauss' law in order to have a proper coupling between the matter and the gauge field terms. So this is also what makes it more challenging to implement in quantum simulation experiments. But I think it's a very, very exciting direction because it's not too far. You can think about techniques to implement these models, and then we would be able to study a much larger class of model Hamiltonians and maybe even dream about connecting to QCD and high energy physics and studying those with a cold atom quantum simulation experiment. Okay, so what's the challenge? Well, we have this matter and gauge fields. So typically the proposals require a combination of fermionic and bosonic degrees of freedoms, which is hard if you need more than one atomic species in the experiment. And we need to realize these local symmetries, which essentially are just governed by Gauss law. So if one particle hops, then the field on the link has to change in the appropriate way, respecting the symmetry of the theory. And that's challenging because this local control we typically don't have. And that brings me back to this idea of having a local control with the tweezer beam. This is done in order to speed up the cycle time, but also to locally try to imprint and impose this Gauss law that we need for the simulation of the system. And I could talk more about the technique that we have come up with, but let me just briefly mention the state of the art. So the main experiments so far that have been performed looked at abelian U1 models in 1D. And because it's very challenging, it's mostly few particle systems. So the first pioneering experiment has been performed in 2016 with 4 ions. And they have looked at particle creation processes in the Schwinger model in 1D, so QED in 1D. And this actually works via a mapping. So it's not the full Schwinger model, including gauge and matter degrees of freedom. The gauge fields are integrated out, which then leaves a model with exotic long-range interactions, which they can implement with gates. And you see here now in 2022, it actually has been extended to 6 ions. But I should emphasize that it's 4 particles, but already this simulation is actually quite complex. So it requires, I think, 200 or 400 gates that had been applied onto the system in order to see this 4 time evolution steps. There's a mapping also to Rydberg atom arrays using Rydberg blockade. Similar model. In this case, it can be mapped to the PXP model and matter fields are integrated out. So here, it's basically the reverse as compared to the ion trap implementation. And there have been 2 other implementations from our group using C2 symmetries and from the group in Heidelberg of Markus Oberthaler, where they have implemented a U1 building block. But this is actually only 2 sites. And more recently, just to complete the story, there has been an implementation with bosonic atoms and tilted optical superlattices, implementing also the Schwinger model, but having matter and gauge field degrees of freedoms. And they work via energy penalties. So this works via mapping onto second order hopping processes. And this has been implemented in larger systems. So this is more or less where we are at the moment, the state of the art in 2022. And what our experiment is trying to do is actually extend this to fermions. We want to have true fermionic matter, have access to both gauge and matter fields, and we want to have a scheme that works in 2 dimensions. And the species that we have chosen, at least in principle, would allow you to also make it non-abelian and connect to more complicated lattice gauge theories. So that's the main idea. And with this, I'm at the end. We will combine lattices and tweezers. So just very briefly, we have a homogeneous lattice system. We add local control, as I've shown for the rearrangement. And then the idea is to locally manipulate the motion of the atoms in a state-dependent way, working with a single atomic species of ytterbium, because it has this nice ground and excited clock states, which then allow us to implement the scheme using a single species. And by that, we don't have to work with mixture experiments. And we are actually quite excited. So the experiment is already half up and running. So we have cold atoms in a lattice, not yet ultra cold, but cold. And we have generated first images of ytterbium atoms that are trapped in such a tweezer array. So here, each individual blue atom is 1 ytterbium atom. The spacing is 5 micron. We can also image the atoms in this trap. Here you see a histogram of a 0 and 1 atom peak. And now what's missing to be done is to combine this tweezer array with our lattice and cool the atoms to the ground state. So we are trying to do both. We're trying to speed up the cycle time. Here we have a cycle time of around 500 milliseconds. And we combine this local control with tweezers for rearrangement and local control of the hopping. And that's the team that is working on this. Here you also see a nice result from our clock spectroscopy, coupling the ground and metastable excited state. And at the moment, the 2 main PhD students working on this are Tim and Etienne. And our proposal for realizing the U1 lattice gauge theory in 2 dimensions is summarized in this recent archive paper that we put online in January. And the pictures from the quantum gas microscope experiment are from the cesium team. Here we have 3 main PhD students working with it right now: Simon Kach, Alex Impertro, and Julian Wienand, and our postdoc Christian, and our master student Ignacio. And here we have also put a recent archive online, which basically discusses the techniques and the reconstruction for this large mod insulator that you see here with more than 2,000 atoms. And we are looking for more people. So when all experimentalists that are out there, please contact us if you're interested. And thank you very much. And I'm looking forward to the discussions.
Okay, thank you very much. Yes, very impressive. Many techniques which I haven't fully understood yet. But okay, so the paper is open for discussion. Any questions? You can freely put on your microphone and make questions as you like. Okay, then shall I? Oh.
Okay, maybe
okay, please.
Okay, I'm just mistaken. But can we also measure the time-dependent correlation functions like an auto correlation functions or dynamic structure factors?
Dynamic structure factors are hard. When you say time-dependent correlation functions, do you mean out of time?
Yeah, so, something like that, or the auto correlation functions maybe, which might have information about an universal hydrodynamics.
Yes, so the easiest is to measure equal time correlations.
Mm-hmm.
There are some possibilities and also measure out of time correlation. And the idea is twofold. So one situation where this works, if you know very well that you prepared always the same initial state. So for instance, you can have an initial state where there's always an atom on site 0. Yeah. Maybe in a thermal background, but you always know that there's an atom on site 0. And then you let the time evolve and measure the correlation function. And this works because then you know that at t = 0, there was this atom there.
Okay. Yeah.
There's another way which makes use of state-dependent potentials. So you can make basically 2 copies of your system. You encode it into 2 different internal states. You can pin one of them and let the other one do the time evolution. And then if you take a snapshot, it gives you access to both the t = 0 and the finite time. And with this, you can also evaluate out of time correlations. It's a bit more complicated, but in certain regions it can be done.
Yeah, but it is difficult to implement. I mean, to prepare the fixed initial state. Okay. Yeah, thanks.
Dustin, please.
Yeah. So my question is about this spacing of the optical tweezers compared to that of the optical lattices. On the tweezer, you said that the spacing of optical tweezers is like 5 micron, right? The spacing of optical lattice is 0.5 micron, right? So how do you deal with this gap between this scale?
Right. So that's a very important question. So there are 2 things to consider. So the first one is about the loading into the lattice. So this is basically what I've shown in one of the previous slides, right? That you first cool the atoms in the tweezer and then you transfer them into the lattice. And what has been shown in this experiment by the Kaufman group is that what you can achieve is a packing of like an atom every other site. So it wouldn't be n = 1, it would be n1/2. But the reason why it is challenging is that if you bring the tweezers close together and you do it with AOMs, then there's a bead between them and it can heat them up.
Right.
But what works is to work with so-called tune-out potentials. Well, I should say it should work because we haven't shown it yet. But the idea is that you can make use of the clock states. So in ytterbium and strontium, you have the ground state and a metastable excited clock state.
Sure, yeah.
You can shelve the atoms into the excited state and apply a potential that is only seen by one of the 2. And then if you take atoms and move them inside the others, they will not see what you are doing. And then they are not kicked out of the trap.
I see.
And for the physics, you're also right. So for the physics, what we're trying to do because we want to locally manipulate the motion of the atoms in the lattice. So that's shown in this schematic down here. This actually only works because we have two different colors, again, for the tweezers, the light blue and the dark blue. And the spacing between neighboring light blue is 1.5 micron. And that's like the smallest you can achieve.
I understand what you mean. Oh, okay. Great, thank you.
So 1.5 micron is doable. Everything below that, I think, is harder.
Yeah. Okay, great. Thank you.
Any other questions?
I have a question.
Okay, please.
So first of all, thank you very much for great talk. So my question is, maybe this is out of your scope, but my question is, can you comment on the possibility of applying your system to quantum computers or quantum memories? I'm asking because, well, first of all, I'm working on quantum information. And another reason is always in your slide, I mean, in the top right corner of your slides, you're showing one kind of figure, like some square lattice, but this looks like surface code to me. So I have been wondering, maybe you are also interested in quantum memories or like application to quantum computer or something. So can you make a comment on that?
Yes. So there are many connections, in fact. So first, let me comment on this figure in the upper right. This figure is actually the extension of our 1D proposal for quantum link models to 2D, to study lattice gauge theories in 2D. And then this is based on a leap lattice type geometry. But indeed, like just visually, it has some connections to the surface code. And there are several connections that I want to mention. So the first one is that in these fermionic systems, if you manage to have this hybrid tweezer lattice geometry that people have done now for bosonic atoms, you can do, for instance, collisional gates. So you can actually move the fermionic atoms around with the tweezer in this lattice. And then the exchange interaction, when two of them come close, can be used for 2-qubit gate implementation. So this would be using a lattice Hamiltonian or a lattice implementation in combination with rearrangement as a quantum information processing platform. So that's one thing.
Excuse me, what degree of freedom are you using for qubit? Is that like Mayonnaise, like topological degree of freedom, or?
No, so in this case, it would be, for instance, the clock qubit, so two internal states of the atom.
Okay, it's something like just spin up and down or something, maybe like similar to this. Yeah.
Right. So in for our specific platform, that would be spin up and spin down, but also in different electronically excited state. So it's actually ground down and excited up, for instance, something like that. And then the spin exchange interaction energy scale can be very, very large in these ytterbium atoms, and you can use that in order to implement a swap gate. So that's one connection that I wanted to mention. There is the second one, which is related, but it actually goes closer to the Rydberg atom platforms that people are working now in many different places around the world. So this array that you see here with ytterbium atoms, if you now add a Rydberg laser, you can do gates via the Rydberg blockade. That's another possibility. The second one, which I recently got a little bit more interested in, is actually using this level structure of ytterbium in order to implement measurement-based protocols. So you see, this is the level structure. So it's a 2-valence electron atom, which has this helium-like structure of singlet and triplet manifolds. This ground and excited state are the ones, the clock states that I have been talking about. But now you can have a nice unitary time evolution in your system, but at the same time, you can implement measurements on the singlet manifold, which would only talk to the ground state, like the 1 is 0 state, but leave coherence in the excited clock state unaffected. And this allows you to implement some of the measurement-based quantum computing schemes that have been developed like already a few years ago.
Oh, that's interesting, but okay, maybe I don't understand, but so if you do some measurement-based quantum computation, you have to do the measurement without distracting the system, right? And but in the usual measurement in the cold atoms, you have to reset everything once you've done the measurement, right? But
yes, here you don't have to.
Oh, okay.
So if this whole development of the platform works as we intend to, then you can do many different things. So first of all, you can make projections where you just, you may kill the G atom, but you project it onto E, which remains coherent and cold in your system. But you can also actually reinitialize the system. So I told you that for this tweezer-based loading of the lattice, you need rearrangement. That means you need to be able to take a picture, but after that, cool them back down to the ground state. This is what we call reinitialization. And using sideband cooling in this lattice allows you to do that. So indeed, we can now think of reusing the same atoms multiple times.
That's
so then you're just limited by finite atom loss in the end.
I see. And how close are you to the this application? I mean, these things.
So at the moment, we have the 2D lattice. So we have atoms in the 2D lattice. What is still missing is to implement the ground state cooling and confine them in a single plane, because we want to have this high resolution imaging access. So if we have more than one plane, that's not good. So that's the two key steps that we still need to implement. I'm still hoping that this year it will be done. So we'll see.
Okay, yeah, thank you very much.
Welcome.
Okay, any other questions? If not, we can probably close the session once and then move on to the chat time, right?
Okay, thank you very much.
Thank you very much.